Hello everyone and welcome to this training session on goodness of fit and contingency tables. My name is Vamsidhar. Whenever we talk about these two words, let me introduce you to one concept. These two kinds of statistical analysis or tests are primarily applicable to a nominal or ordinal data. What is this nominal or ordinal data? We have discussed earlier that the data is more categorical, not in the form of a ratio scale. So the data, whatever we want to analyze, the variables, whatever we would like to analyze, they should be categorical in nature. They should be the names. They should not be the numbers like heights, weights. They should be the names like gender, male, female. Response to a question, yes, no. So if at all any particular attribute is more in a categorical form, either in a nominal scale or an ordinal scale, I would be looking forward to do the detailed analysis of them using the mechanisms of goodness of fit and contingency tables. If at all my data was a ratio scale or a scale kind of numbers kind of quantitative kind of a data, we have been talking about so many aspects till now. We have talked about testing for proportions, we have talked about testing for means, we have talked about testing for standard deviations or variations, and we have talked about correlations, regressions, we have talked about between two samples, the equality about proportions, equality about variances. We have done so many tests till today across various chapters. But when it comes to our particular data being a categorical or a qualitative data like the genders or responses to a question or marital status or did this particular treatment cure the disease or not, so where the answers would be more of textual and finite in number, which are typically called as categorical, which will fall into either nominal scale or the ordinal scale. On such kind of data, if I want to do some analysis, we are using these two concepts. So typically I can very well say that this chapter is primarily addressing the categorical data analysis, or I can say qualitative data analysis. So look at it from that standpoint and we'll take it further. So we would be discussing about three kinds of data: goodness of fit, which is generally associated with one variable at a time, right? One variable, and I want to test the proportions, which means the percentage distribution of a particular value across the samples. So one variable, I'm looking at the proportions. I'll talk about it in slightly detail. Here I'm talking about two variables which are independent, and here I talk about two variables which are more dependent and are matching, or generally we'll have only a 2 by 2 kind of a table output for them. So yes or no, yes or no, that's a kind of tables we look at. Only two outputs for every value. If such is so, more on a dichotomic kind of data sets is what the McNemar's test for matched pairs will be working, and they should be pretty much matched kind of a data. So that is one more aspect that needs to be looked at from the McNemar's test kind of a perspective. So these are the three different analysis we would be doing on the categorical data. Now let's go one by one. If my objective is to test the proportions of data, typically if I say that my claimed distribution, in a claimed distribution, I want around 30% to be graduates, around 20% to be in a particular company. I'm making a claim that 30% of them will be graduates, 20% of them will be postgraduates, and the remaining 50% of them will be PhDs, doctorates. This is the claim which I have. Now, I want to prove statistically whether this claim is correct or not, whether this claim can be made or not. So, what is that I am doing? I'll take a sample of people in a company and I'll gather their qualification, whether they are graduates or postgraduates or doctorates. So, from the sample, what the proportions I am getting, let's say I am getting 25% to be graduates, 40% to be postgraduates, and 35% to be doctorate. So these are my observed proportions, whereas these are my expected. Expected is claimed. Whatever I am claiming, so that is what is my expected. So let's say I am going with 100 people. I should get 30 to be graduates, 20 to be postgraduates, and 50 to be the doctorates. But when I have collected the data, I got 25 to be graduates, 40 to be postgraduates, and 35 to be doctorates. Now, using this information, I have to say whether my claim, whatever I am making, is statistically significant or not. So in that case, where we are only counting, where the analysis is more about the frequencies of the various categories in a sample of data and comparing it with the expected kind of frequencies. So whenever I have an observed frequency, whenever I want to make a claim that this should be the proportion of each of these different data sets. For example, uh, in a set of every 100 people at a particular organization, I need 20% doctors, 30% someone else. So if I have such kind of a data and if I want to see whether my claim is more valid or not, I will do this kind of analysis. So now on the 100 data set, this is my expected frequency and this is my observed frequency. So to test out whether the statement is significant or not, the test statistic which we are using is a chi-square statistic, which I'll use by this kind of an equation. Observed minus expected whole squared by expected. So observed is 25 minus expected is 30 whole squared by expected 30 plus observed minus expected whole squared by expected and observed minus expected whole squared by expected. This is what is the chi-square statistic for me. And obviously this chi-square statistic has to be compared against the critical values. What would be the critical values here? Because I have three data items, the critical value, the degrees of freedom will be equal to 2 because the sample size 3 groups of data are there. So if there are n categories, n minus 1 will be my degrees of freedom. So there are 3 categories of data here. So corresponding to 2 degrees of freedom and probably 5% level of significance, I'll find out what is the critical value corresponding to the chi-square. And because we are testing the null hypothesis as uniformity between observed and expected. So the alternative will always be there is no uniformity, and we are talking about a two-tailed test, because the alternate hypothesis is not equal kind of stuff. So because it's a two-tailed test, I will check whether my computed chi-square statistic is lying within the critical region, and if it is within the critical region, I will reject the null hypothesis and say that the claim is not a valid claim. Otherwise, I'll go ahead saying the claim is a valid claim. So this is the way I test the proportions as per a claimed proportion. If I'm so whether the claim which I am making about the proportions of the various categories in any particular data set is correct or not. So that is what is my intention when I am doing the goodness of it. So some of the main requirements for it, I need to collect the sample in a random fashion, and for each of the categories the frequency counts have to be separate, and the expected frequency should be at least 5. Here we are having 30, 20, 50 to be the expected frequencies, but if the expected frequencies come below 5, it's better to club that category. Any expected frequency that is going to come below 5, please club that category, because we are using the discrete data to convert it into a continuous data, approximating it to a chi-square distribution. So the chi-square distribution will be more and more effective only when I have a minimum of 5 as a part of my expected frequency. So for whatever in observed frequency, there is no limit. Even if I have 2 or 1 as the observed frequency, don't bother about it. But as a part of the expected frequency, because expected frequency is there in the denominator for the computation of the chi-squared, the value will be biased very heavily if the expected frequencies are much lesser. So the requirement is make sure that the expected frequencies are at least 5, and then you can either use a comparison with the critical values, or you can your system software can generate the p value, and you can compare the p value against the level of significance to take your decision. So that's the way we use the goodness of it, especially one single variable. If I have made a claim about their expected proportions of the different categories in that data, I would like to see whether the data which I have collected is more or less the same, or has it significantly changed. Then if I have to do that such kind of comparison across two variables, so let's say I am talking about the multiple stores which are there, and also the satisfaction levels of the people across the stores. So if I want to find out, is there any kind of dependency between the store and the satisfaction level? See, for every person, I will highlight which store has he visited, and is he what is his level of satisfaction about that store. Highly satisfied, moderately satisfied, not at all satisfied, such kind of scale. So there are two variables which I am capturing for every customer. What is the store he is visiting? Store 1, store 2, store 3, store 4. Which kind of store is he visiting? And what is his satisfaction level across that store? So these are the two variables I am taking. And I would like to analyze, is there any kind of dependency between these two variables? Like, probably, is there any kind of an output which says store 3 guys are heavily satisfied, whereas store 2 guys are heavily dissatisfied? So I would like to do that kind of an analysis. Here also, if we see, both the data are categorical. I'll just find out which store. So the values will be either store 1, store 2, store 3, store 4, not a numerical value, not a quantitative value. Similarly, when I talk about satisfaction levels, it would be more like highly satisfied, moderately satisfied kind of stuff. Even that would be a, a, a categorical value itself. There is no number directly assigned to it. So in those kind of cases, when two variables which I am analyzing together are in the form of categories, then I can still resort to this contingent table approach, especially if I want to test for the independence. What is the meaning of independence? The different stores, there is no specific relationship between the stores as well as the satisfaction levels, which means there is a uniformity in the satisfaction levels across the various stores. If that is the kind of testing, or is there any kind of a difference in the satisfaction levels across the store? Here my intention is not to say in this store are people are highly satisfied or not. That is not my intention. Then it becomes a one variable analysis. Probably there, okay, if I am I getting 10% of highly satisfied customers, 30% of moderately satisfied customers, something like that, then I can resort to my goodness of fit approach, which I have discussed in the earlier slide, because it is only one variable analysis. If I want this proportion of the people under each of the categories, then I can use a goodness of fit approach. But here I am not interested in one variable. I am interested in taking two variables together and then observe, is there any kind of dependency across these two variables, which means, as I said, is there any difference in the satisfaction levels across the stores? If that is the kind of question I would like to address, where I have collected the data relating to the store which the person commonly visits as well as his satisfaction level across that particular store, then we can use this contingency table approach. Here also, first I make it as a table. Okay, this is the table. These are the stores and these are the satisfaction levels. So here is what we put up, the observed frequencies. Okay, from store 1, how many of them are highly satisfied? This is the observed frequency. So we'll have observed frequencies at each of the layers like this. These are the various observed frequencies like this. Now I need expected if I have to use the earlier. So here the two-dimensional table, I will first convert it into a one-dimensional table. So just like the way we have made the earlier table, now all these items will get converted into a one-dimensional table wherein all these are different observed values. Here the only difference is the expected values will not be given as a claimed values. The expected values are directly found out by this mechanism. The row total into the corresponding total divided by the grand total. Now if I say these are my number of customers at each of the layers, let's say 3 stores, right? 3 stores and satisfaction levels A, B, C, D. Very good, good, whatever it is. Now this is the frequency, observed frequency. Whereas how do I get the expected? I'll find this particular row total, 9 plus 5, 14 plus 1, 15. The corresponding row total, 10. And the total, grand total. Okay, what is the grand total? This is 10, 15, 20, 26. And here it is 42. Yeah. So 10 plus 42, 52 plus 12, 678. Now the expected frequency for this part will become 15 row total, column total into the corresponding row total divided by the grand total, 150 by 78. So somewhere around 2 is the expected frequency for this particular outcome. Same way I can do for all the 12 possible blocks, and those are what the expected values. And after that the chi-square analysis is still the same, the chi-square, but the degrees of freedom in this case is number of rows minus 1 into number of columns minus 1. So there are 3 rows and 4 columns, So the degrees of freedom will be 3 minus 1 into 4 minus 1, which is 2 into 3, 6. So the degrees of freedom in this case will be 6, and corresponding to the 6 degrees of freedom and a 5% level of significance, I will check out for the critical value and then compare my computed chi-square value with the critical value depending on whether it is falling in the critical region or in the not critical region. I would either reject the null hypothesis and say there is some kind of dependency. There is no uniformity across. There is no independence between the row variable and the column variable, which means there is some level of dependency between the row variable and the column variable. But if I am getting chi-square not lying in the critical region, I will go with the null hypothesis. So there is an independence between the row variable and the column variable, which means there is a uniformity across all the there is a uniformity across the satisfaction levels across the various stores. It's not equality. Uniformity does not mean equality. The distribution of the satisfaction level across all the stores, there is not much of a difference. So it will be used very well to test the homogeneity in the data, whether there is too much of a difference between the various values across the row and the columns, or it can help us in testing the dependency or the independency between the variables. So especially when I am looking at two different variables together, and the two variables are independent variables, when I am looking at those two independent variables, we can get into this process of contingency table, which also uses a chi-square test for taking the decisions. This also uses a chi-square analysis and a chi-square test, which will give you the final degrees of freedom, and based on the degrees of freedom you can evaluate whether there is some level of dependency between the row variable and the column variable. There are, again, this is also a very common tool because very few tools are available while assessing the categorical data, and this is one such powerful tool trying to find out the relationship between two variables which are categorical. It's as good as, it's an equivalent to correlation analysis on your quantitative data, trying to find the relationship between the two quantitative variables. Whereas when I'm trying to find out the relationship between two qualitative variables or categorical variables, we are resorting to this contingency table analysis. Some softwares also use a term called crosstab analysis, because you are doing a tabulation of the different frequencies of variable 1 versus variable 2. You are taking the two variables together and then creating a cross tabulation of that, and after that trying to check out for the independence or homogeneity of between the two variables. So that is where this is also called as a crosstab analysis, but the typical statistical term for it is the contingency tables mechanism. Then one more test which I am more interested in is a McNemar's test, a small adjustment to our contingency tables approach, or probably a special version of the contingency table approach. The two things that are adjusted there are, it should be a 2 by 2 table only, like this: cured, not cured, cured, not cured. So there are two variables, and both these variables have only two outcomes. Both are dichotomous variables. So it's as good as, okay, on a person, I have tried two treatments. So for each person, we have given two treatments, X and Y, and we are seeing whether the treatment, which of the treatments have worked on each of the person. So there could be some cases where X has worked whereas Y did not work, or X has not worked and Y has worked. So we'll find, so they are matched pairs. You remember the same thing has been applied on a person. Two different treatments have been applied on a person, and I am more interested in checking this kind of proportions. Generally, it is used for checking this kind of proportions. The proportion where one has been successful whereas the other did not, right? Because I'm talking about treatment X and treatment Y. In some cases, the samples could be completely different. So in some guys, I would have found that the treatment X would have not cured, but Y would have cured. In some cases, I would find that Y has cured, Y did not cure, but X has cured. So if I go with this kind of matching pairs and establish that frequencies in this form, two variables, the two outputs of one variable here, two outputs of another variable here, generally giving yes or no kind of meanings, right? Cured and not cured, yes and no. So if at all I'm looking at the relationship between this B and C to be specific, the relationship between B and C, the proportion of the frequencies of B and C are the same. What is that B and C? One is yes, the other is no, because we are talking about the matching between those two, the resemblance between those two sets of variable. So wherever I want to do this kind of analysis, okay, one is successful compared whereas the other is not. I want to see whether the frequencies of these two kind of data sets is more or less the same. I can resort to this McNemar's test for matching pairs. And few things that needs to be done for this particular test is, this is also a chi-square test which goes with this particular kind of a statistic. B minus C, right? So which is the number of people who have been cured by one and not by the other versus cured by the second one but not by the first. So because there is a modulus of it, it hardly matters what you take as B and what you take as C. Minus 1 whole squared divided by B plus C. This is what will follow a chi-square distribution. And now what we are saying is, this you compare it with your critical value, which is having a degree of freedom of 1 and your level of significance of 5%. Again, if this is lying in the critical region, reject the null hypothesis and go with the alternate, saying that there is a difference between B and C. But if you are getting the value not lying within the critical region, then you can very well say that you can fail to reject the null hypothesis, and you are saying the statement there is not much of a difference in the frequencies between proportion of the frequencies between B and C, which means there is not too much of a difference between the treatments of X and Y. So if at all I want to say is X curing much better compared to Y or vice versa, that this kind of a test will help me in a much better way. And a couple of things that are very much important for running this test is, the frequencies of B and C should come from different pairs, which is nothing but the not cured of one section but the cured of another variable, whereas cured of one variable and not cured of the another variable. So such kind of different pairs if I am getting, then only there is much meaning to this McNemar's analysis. And so this is more like a sophisticated or a simplified version or a specialized version of of your contingency table analysis, where you can get only two possible outputs for each of the variable, and you are trying to test the 2 by 2, and the degrees of freedom is 1 because row minus 1 into column minus 1, that's the degrees of freedom as we have discussed earlier. So 2 minus 1 into 2 minus 1 will bring out the degrees of freedom to be equal to 1. So these are the three common kind of mechanisms that are used to test for the proportions of data in which is more categorical in data for categorical in nature. If I am talking about only one variable against a particular claimed proportion, I will go with goodness of fit approach. If I am looking at the independency or homogeneity between the two variables, then I'll go with the crosstab approach. And if I am testing the uniformity in the proportions of the frequencies in a 2 by 2 kind of a table, which is more from a discordant pairs of data, matching pairs of data, that is what we are applying a McNemar's analysis using a chi-square analysis. So these are the three things you should be comfortable the moment you are seeing the data to be categorical or qualitative in nature. If you have any further queries regarding this, I suggest you can give me a call on the number below 98480 I You can also drop in an email to me at vamsidhar@pacegurus.com. I suggest you to visit my website www.pacegurus.com to get updates regarding the training and consulting assignments, as well as the training videos in the areas of finance, analytics, statistics, and investments using tools like Excel, VBA, and SPSS. Thanks a lot for listening to this session. Thank you very much.